What is so confusing about enzyme inhibition? Modern inhibition equations that define drug research are wrong. These equations, when derived, failed to make the distinction between the chemical equilibriums for the formation of enzyme inhibitor complexes and the actual effect the inhibitors have on the enzyme. The failure to make this distinction is linked to how the inhibition term is expressed in these equations. The inhibition term in these equations does not appear as a classical binding association term, which obscures its only function as a term defining the formation of the enzyme and inhibitor complex. By rearranging this term into a format that shows its true function, we can identify the processes the inhibition equations actually describe and the problems associated with each equation. So, join us as we investigate the failings of inhibitory theory by looking at problems associated with the use of the classic inhibition term and discuss the straightforward way of fixing these problems. The derivation of the Michaelis-Menten equation represents only a slight modification of the equation used to describe receptor interactions. Ligands and receptors come together to form complexes based on basic chemical equilibria. This is the same equilibrium interaction observed between an enzyme and its substrate. The only difference between the two processes is the enzyme-substrate complex has the chance of producing a chemical reaction where the enzyme catalyzes the conversion of substrate to product. This chemical reaction is what distinguishes the Michaelis-Menten equation from equations used to define ligand-receptor chemical equilibriums and shows up as a single term called the Vmax in this equation. The Vmax is the maximum catalytic rate for substrate conversion to product. And here, when we multiply it by the chemical equilibrium term, that defines the fraction of the enzyme population found in the catalytically active enzyme-substrate complex. We get the rate of product formation produced by the enzyme population being studied. So, as we can see when describing enzyme kinetics, we can't simply rely on the formation of the enzyme-substrate complex. But we also need to introduce a term describing the chemical reaction that can occur when the enzyme-substrate complex is formed. While this is a simple idea, and you may be wondering why we are spending time distinguishing the difference between a chemical equilibrium term and a rate term, this distinction must be emphasized, as this is precisely where the idea of inhibitor interactions went wrong and derailed the development of drug theory. The failure of enzyme inhibition theory can be attributed to issues associated with the derivation of the basic enzyme inhibition equations. When deriving the Michaelis-Menten equation, you need to combine several parts. A rate equation for the chemical reaction, the chemical equilibrium term defining the propensity of the enzyme and substrate to come together, and an equation defining the states the enzyme is found in. From this, you can easily see how the term describing the formation of the enzyme-substrate complex must be modified with the rate equation to define conversion of substrate to product. However, when this derivation is modified to include inhibitors, we encounter the main issue. Derivation of the inhibition equations use similar components to those required for the Michaelis-Menten equation, but with the obvious inclusion of the chemical equilibrium terms used to define the formation of the enzyme inhibitor complexes. This inclusion of terms describing the formation of enzyme inhibitor complexes results in equations which are similar to the Michaelis-Menten equation but contain new chemical equilibria terms for the binding of the inhibitor. If you look at these inhibition equations, the presentation of the inhibitor binding term is non-intuitive, as they do not look like a regular chemical equilibrium term. So at this point it must be stressed, as it is at the root of the issue associated with these derivations. The terms describing the inhibitor interactions in these equations only describe the formation of enzyme inhibitor complexes and do not provide any information on effects the inhibitor may have on the activity of the enzyme. However, the commonality of the inhibition term between these equations has provided a false confidence in their validity and has continued the use of these equations in research and drug characterization to this day. But let's take a closer look at each of these equations and see how their inhibitory terms affect the Michaelis-Menten equation. As we can see by looking at the Michaelis-Menten equation, enzyme kinetics is a composite of two different processes. the coming together of the substrate and the enzyme, quantified with the substrate affinity constant, and the catalytic conversion of substrate to product, which is quantified with the Vmax. Inhibition can affect either of these processes, or more commonly, inhibition can affect both at the same time. As such, three equations were developed to describe these different types of inhibition. The competitive inhibition equation was proposed to describe inhibition affecting the substrate affinity. The non-competitive inhibition equation, alternatively, was proposed to describe inhibition affecting the catalytic conversion of substrate to product, and mixed inhibition was proposed to affect both. You can see the same inhibition term in the competitive and non-competitive equations, which provides the misconception that this common inhibition term supports the correctness of these equations, and this assumption is probably reinforced by the presence of similar terms in the mixed inhibition equation. But this is completely misleading. If we focus on the competitive and non-competitive equations, in the case of the competitive equation, inhibition is believed to affect substrate affinity, and that is reflected by the Km being multiplied by the inhibition term. However, the non-competitive equation strictly affects reaction rate, so inhibition should only affect the Vmax in this equation, but in contrast to the competitive equation, the Vmax is not multiplied by the inhibition term, but instead is divided by it. Right here, it becomes quite apparent that the inhibition term does not affect these processes in a similar way, but the failure to complete the derivation of the inhibition term obscures what that effect is. By leaving the inhibition term in this form, the non-competitive inhibition equation obscures the inhibition term's relationship with the inhibitor equilibrium term used in its generation. Generally, in biological models, equilibrium relationships are represented with equations for binding curves, such as the Michaelis-Menten equation, IC50s, or ligand-receptor binding curves. The inhibition term found in the non-competitive equation can also be represented in a similar manner, revealing its actual effect on the reaction rate. So if we complete a simple rearrangement of this term, an inverted term that describes the fraction of the enzyme population not bound to the inhibitor appears. We can now divide the Vmax by this term, ending up with the fraction of the enzyme population not inhibited by the inhibitor. This form of the equation demonstrates that the non-competitive equation describes a state of complete inhibition, where the binding of an inhibitor to an enzyme blocks its ability to convert substrate to product, meaning that the inhibitor chemical equilibrium term defines the fraction of the enzyme population that is completely inhibited. This is the only result that could be expected by simply incorporating the inhibitor's chemical equilibrium term into the derivation of the non-competitive inhibition equation. And this is the other problem associated with the non-competitive equation. As mentioned before, the effect the inhibitor has on an enzyme is not defined by the propensity of the enzyme and the inhibitor to form a complex. But the inhibition term in its classical form makes it difficult to recognize or fix this problem. In this rearranged format, which reveals the inhibitor binding curve, we can easily add a modifier to define the effect the inhibitor has on the enzyme. This small change produces a much more useful equation, changing it from an equation that only defines complete inhibition to one that can define any degree of potential inhibition or activation of the enzyme's catalytic rate. In contrast to this simple, useful adaptation of the base non-competitive inhibition equation, the problems with the competitive inhibition equation become quite apparent, rendering it almost useless for describing changes in substrate affinity. Doing the same rearrangement of the inhibition term in the case of the competitive inhibition equation results in the substrate affinity term getting divided by the fraction of the enzyme population which is not inhibited by the inhibitor. This makes no sense, but is in line with the nonsense used to define this equation. Substrate affinity is a chemical equilibrium related to the ability of the substrate and enzyme to come together like a ball being caught by a glove. If you wanted to reduce the chances of catching the ball, you could alter the properties of the glove. For example, you could add something slippery like oil to the surface of the glove, or you could give the glove to someone less experienced with catching a ball. This reduces the probability of catching the ball, but doesn't exclude the possibility it could happen. In contrast, the competitive theory states that this is not how changes in substrate affinity occur, but rather changes in substrate affinity only occur when there is an inhibitor that completely blocks substrate binding. Or, using the glove analogy, changes in substrate affinity only relate to situations where you already have a ball in the glove, preventing the glove from catching another ball. The other tenet of this theory is that a competitive inhibitor causes a linear change in substrate affinity, which is what the traditional inhibition term describes in this equation. As an inverted binding curve, the inhibition term used here is a straight line, which is not surprising as the inversion of binding curves have been used for almost a century to simplify the modeling and data fitting of the Michaelis-Menten equation. This graphical approach was helpful before computational analysis was easily accessible, because linearization simplifies the determination of the constants found in the Michaelis-Menten equation, as the substrate affinity and maximum velocity are now defined by intercepts on the x and y axis. But this common practice was not enough to clue researchers into the true nature of the inhibition term found in the competitive inhibition equation. Changes in substrate affinity should reflect a shift between two states, and the observed shift between the two affinities must relate to the fraction of the enzymes found in each state. Therefore, paralleling the effect of inhibitors on the maximum velocity in the non-competitive equation, we can multiply the change in substrate affinity by the fraction of the enzyme population bound by the inhibitor, directly linking changes in substrate affinity to the formation of the enzyme inhibitor complex. Once this link is established, it is once again simple to distinguish between the chemical equilibrium and the effect the inhibitor has on the enzyme. For the full derivation of this equation, you can check out my previous video on the derivation of the competitive inhibition equation. Now that we have equations for describing inhibitors that can affect the reaction rate or substrate affinity individually, it's probably a good time to restate that inhibitors that affect one or the other are in the minority, and it's much more likely to come across an inhibitor that affects both properties at the same time. Inhibitors that affect both are usually described using the mixed inhibition equation, but the same problems that occurred with the competitive and non-competitive equations also plague this model. In this case, the failure to recognize the true nature of the inhibitor equilibrium term resulted in an equation with two inhibition terms. One, paralleling the use of a regular binding curve, like the one found in the non-competitive equation, and the other, an inverted binding curve, as is found in the competitive inhibition equation. Directly relating to the presence of these two inverted inhibition terms, data fitting to the mixed inhibition equation requires two distinct inhibitor binding constants that cannot be equal, or it reverts to the non-competitive inhibition equation. This means that theoretically, for this equation to be correct, we live in a reality where an inhibitor must bind to the enzyme twice but separately, in different concentration ranges to produce the inhibitory effects. Once for an interaction that affects the substrate affinity, and once for an interaction that affects the maximum velocity. This is justified by the idea that changes in Km, like the competitive inhibition equation, are related to the inhibitor binding the enzyme alone, and changes in reaction rate are produced by inhibition of the enzyme substrate complex. This implies that one binding interaction cannot affect both properties at the same time. The issues with this equation are only compounded by the problem that in the derivation of the equation, just like the competitive and non-competitive equation, only the inhibitor equilibrium binding terms are used to describe the effect the inhibitor has on the enzyme. Additionally, there does not appear to be a way of rearranging the mixed inhibition equation into a format that would allow the user to fix this problem. However, the solution to this problem is easily achieved by replacing the mixed equation with an expression that combines the equations we used earlier to replace the competitive and non-competitive equations. In this equation, we have a better solution, where the inhibitor equilibrium binding term is presented in a form that can be easily modified to describe the change in enzyme activity produced by the inhibitor binding. Additionally, as neither of the inhibitor binding terms are inverted, a single inhibition constant can be used to model the changes in substrate affinity and reaction rate. And yes, this equation can also be derived in the classical way, although I will leave that for an upcoming video. So by now you may have noticed that the solution to this problem is a simple expansion of the Michaelis-Menten equation, which includes binding curves, defining the inhibitor's interaction with the enzyme, and modifier terms, which describe the effect the inhibitor or activator has on the enzyme. This simple equation shows that in the end, everything is a binding curve, which holds wonderful implications for modeling complex biological interactions, as this equation can be used as the root for iterative expansion and may hold the key to a unified system for describing enzymatic modification, something we will get into in future videos. But in conclusion, the use of the classic inhibition term, 1 plus the inhibitor concentration divided by the Ki, represents a failure to recognize the difference between the enzyme inhibitor chemical equilibrium term and the effect the inhibitor has on the enzyme. This problem has confused biological modeling, hindered progress, and sidelined the role of enzyme kinetics in biological studies. However, by clearly distinguishing between the propensity for inhibitor complex formation and the effect an inhibitor has on its target, these theories have the potential to shed new light on the processes of life and may lead to the medical breakthroughs that have been elusive for far too long. And I don't say that lightly, as I will be covering my theories on Alzheimer's disease based on the application of these models in upcoming videos. If you would like to learn more about the problems associated with enzyme inhibition, you can check out my preprint, The Fundamental Problem with Enzyme Inhibition Theory, recently posted on Qeios through the link below in the description. But for now, thanks for watching, and I hope you will subscribe and stick around for future videos.